So what I'd like to talk about today is the issue of security and cybersecurity in an industrial context. And this is very important for the development of the fourth industrial revolution. It is a showstopper if we cannot get this right. If we are unable to manage security, then anything we invest in this industry could easily come to a halt, because we cannot control when things will work, when things won't work, and when things will work in an unpredictable manner. I'd like to, it's great to be speaking to you today. I very much enjoyed my visit to Bangladesh before the COVID outbreak, and I share fond memories of that session. And I'd like to thank Dr. Fatah for inviting me to give this presentation. I very strongly support the work of your institution, and as I say, I'm very pleased to be here. What I want to do is to just talk about a couple of different aspects of cybersecurity today. And firstly, I want to talk about the difference between cybersecurity in an IT setting or a computer setting and cybersecurity in operational technology or OT setting. I want to say a little bit about critical infrastructure, and I want to point to a couple of examples of what we can do to help protect our infrastructure and to help facilitate the adoption of advanced technologies. For myself, I work in the transport industry. I'm a Chief Information Security Officer in the transport industry in Australia, and I've worked with cybersecurity for nearly 30 years. And so this is an area that I'm very passionate about. When we talk about operational technology, for those in industry, this is a well-known term. So information technology refers to the computer systems that, for example, could run our HR or our finances within a company. Within the heart of an industrial company, however, is its industrial production. And here we're not talking about information technology, we're talking about technology in the physical world, and that is operational technology. So the examples of operational technology could be SCADA management systems, control systems, measuring devices such as smart meters, and any of the sensors or actuators that relate to industrial IoT. If we look at, and this is just a random slide, I'm not asking you to pay attention to the detail, but just to give an idea, when we look at the power industry, all elements within this diagram here sit within operational technology. So these are not systems that are recording the number of staff or people's pay. These are systems that are keeping power flowing, that's enabling power to be generated, that's measuring power, it's being distributed. So operational technology and information technology are different in many ways, but from a cybersecurity point of view, they have a fundamental difference, which is the priority which we apply to the two areas. So within information technology, we have what we call the CIA triad: confidentiality, integrity, and availability. And these mean confidentiality is keeping things secret, integrity is making sure things don't get changed, and availability is in its common use, and making sure you have it in front of you. Within operational technology, that priority is reversed, and we actually begin with reliability. Because in operational technology, the single most important thing is safety. Whether it's measuring, whether it's an actuator in a water system, which could be releasing water in a dam, or a sensor which is determining when an industrial process is becoming dangerous, or when it's going outside of its normal measurements. These are things that can result in enormous disasters for people if they're not managed properly. So we start with OT, we start off with reliability, and then availability. We want to make sure the system doesn't get isn't disabled, and then integrity, and then finally confidentiality. So within operational technology, the traditional way to achieve cybersecurity was to have physical isolation. So you don't connect, in the case of medical devices, you don't connect the medical devices to the internet or to a network in general. Since then, since the 1990s, isolation has become replaced by segregation. That is the idea that different parts of the network, the OT sits in a very separated part from IT. Unfortunately, segregation in turn is becoming segmentation. So instead of having a well-defined separation within your network, now you may have simply different devices running off different VLANs. And if we think about that, the whole people who are familiar with cybersecurity and with programming devices, cybersecurity devices, will realize how easy it is to misprogram something. If we're simply depending on segmentation, some delineation between two adjacent virtual LANs, then all we need is one misconfiguration, and that segregation is lost, and suddenly our systems, in my case, say the traffic light systems, could suddenly be exposed to attack. Now, I want to say a couple of things about why the internet is so insecure. And I'll make the claim is that this is the way it was designed. This is not an accident. This is not bad engineering. This is how it was actually designed. So if we go back to the foundations of the internet protocol, which is packet switching, the inventor of packet switching, Paul Rand, in the early 1960s, prepared a series of descriptions of how packet switching would work, which was then adopted when the internet was created. In 1964, at the end of all the other reports, he produced a report saying, you must think about security, and security is not something you can add on at the end. When his ideas were taken up by Vint Cerf and others in designing the internet, they failed to pay attention to this, and they decided that security wasn't necessary, and therefore they didn't build it in. 20 years later, in 1989, so the first packets were generated in 1969. In 1989, Tim Berners-Lee designed the World Wide Web. And at that stage, when he filled out the template, requesting funding for his plan, he said that two things weren't required, and they were copyright enforcement and data security. So you can see from this that the fact that we don't have security in the internet or in the World Wide Web is because that was the intention of the designers. They didn't believe it was necessary. So that's a tiny bit of background. I just want to talk a little bit about critical infrastructure. And this is the connection to industry. And I want to give the example of the energy sector, which is an area I've worked in. Now, this is a US website. It's called the Cybersecurity and Infrastructure Security Agency, and they're concerned with various different aspects of critical infrastructure, and they have been since about 2012, when President Obama issued an instruction that we should be looking at that we should be addressing vulnerabilities within critical infrastructure. Now, within the power industry, we have something called the Purdue model, and this was designed in the 1990s, and it wasn't originally meant to be a way of protecting security, but it became adopted for that purpose. And it's a fairly logical model and quite a useful model. So it says at the bottom we have the sensors and actuators, and this is very much the IIoT that we all know. These devices are connected back to programmable logic controls, PLCs, that do the basic controllers and aggregate these sensors and actuators. These are then behind a firewall. We then have the supervisory control, which oversees all the PLCs and collects all the data from the sensors and issues the instructions to the actuators. We have a further firewall, and then we get to the threat management area. So this is supposed to be the area that protects the OT area from the IT area. Above that, we have the industrial demilitarized zone, another layer of protection in there. And then at the top, we have the IT area going off to the internet. And the idea of this structure was that the internet up the top is a long way away from the sensors and actuators sitting down at the bottom, and is very well protected by several firewalls and several layers of security. Now, the problem with the Purdue model is that it doesn't allow for IoT. So down here, these sensors may be they may be smart meters connected via wireless connections, which are sensing the amount of energy or the amount of water that's traveling through a particular thing. So what happens here is the IoT down here becomes a point of vulnerability. So you've protected everything all the way down here, but at the bottom, you've opened yourself up. And there are tens of billions of devices in the world today, tens of billions. And the vast majority of these are poorly protected. So this means IIoT, industrial IoT, dependent on the IoT protocols and practices and architectures, is fundamentally flawed as a security if one uses the Purdue security model. So this is another way of explaining that. The dream of IoT was that all of these devices, everything would be connected up. Everything would have a way from the lights in your house, your refrigerator, your phone, and a whole lot of other devices. The actual reality, and I like this diagram. So this is the Internet of ransomware things, and what it's suggesting is that all of these devices, all of these smart devices, suddenly become part of what in cybersecurity we call the attack surface. And the more devices you have, the more ways you can be attacked, the larger your attack surface. And some of them are hungry, I'll pay up and I'll unlock my door. So it's the fridge telling the person that they're going to hold the food inside the fridge to ransom, and so forth. I like this diagram a lot. Now, I just wanted to talk about some of the examples of problems that occur, because when I asserted before that we can't have advanced industry based using, for example, virtual reality and a whole lot of other techniques that are going to be important, we can't have that if the area is vulnerable. When we look at what's happened over the last 12 months, or the last 24 months, we saw the Colonial Pipeline incident in the US, where the hackers attacked the finance system and held the finance system to ransom. But the way that they did it meant that the company could no longer safely run its OT systems, which was providing fuel to petrol stations around over a large area across the East Coast. So effectively, the ransomware of the IT system resulted in the unavailability of the OT system. And I've then one point that I like to make is that sometimes people think that because their IT systems and their OT systems are separated in their company organization, that this in some way provides them with some sort of protection. If you've got no relations between your IT team and your OT team, that doesn't mean that hackers don't. And there's a couple of very good examples there. Stuxnet, where an IT thumb drive device was used to attack an OT centrifuge environment. And in the other case, the fish tank in the casino, where the OT fish tank was a source of attack on the IT system, the data records of the casino, resulting in the loss of significant amounts of money. And I just want to finish with a couple of general points about how some of the things that we can do. Now, firstly, and this is very short. Firstly, the way we think about cybersecurity is very important. And that one of the principles from the rail industry, and I work in the as I said, I work in the transport industry, which includes rail, is that we have this principle that says if it's not secure, it's not safe. And this is a very helpful way for people in industry to think about cybersecurity. So if people in industry think, if they put cybersecurity into the safety bucket, and they think, oh, okay, that could kill people, not just we may have ransomware, but that could initiate some safety disaster, then it's not just that they're going to pay more attention to it, but they're going to be able to think of it in a way that they're used to thinking. So they're used to thinking about safety. And if we say, okay, cybersecurity is part of safety, and then they'll say, oh, okay, yeah, that makes sense. So we've got to be careful about this and this and this. And that will give them an immediate advantage in thinking about it. A second area is the field of zero trust architectures. Now, I pointed out that the Purdue model is not very helpful at the moment because of IoT devices, insecure IoT devices connected as sensors, actuators, and so forth. And one way to approach this is the approach of zero trust architecture. And ZTA basically says you don't trust something purely because of where it's come from. And this is a very important principle in cybersecurity in any case. So just because the CEO tells you to make a payment, that doesn't mean you should make the payment, because somebody could be impersonating the CEO. And this is a major source of attack, and it's cost companies tens of millions of dollars on occasion. And the third one is human in the loop. And this is a very important principle. People often don't think of this in relation to advanced industry. But the way I'd suggest it works is as follows. So technology can do stuff really fast, certain things really fast. And it can do it very, very thoroughly. Like if you told a person, check these 10,000 boxes, the person may or may not manage to check all the 10,000 boxes. If you say to a computer, and you've appropriately programmed it, check these 10,000 directories, it will get that right. So, or check these 10 million directories or 10 billion directories. So for a computer, that's not hard at all. What technology, and particularly AI, lacks is common sense and the ability to consider what is unexpected. And in both of those cases, both of those cases are important when we think about cybersecurity. And so what we should do in relation to cybersecurity, and this is a more general statement about use of AI in general, is we should use it to augment humans, to help us do those things which we're not so good at, to alert us when we may be about to make a mistake, to lighten our burden. But we shouldn't use it to replace human capacity, because maintaining human capability in the things we do is extremely important. Because otherwise, if we say throw up our hands and say let the machine do it, it's effectively just constantly throwing the dice and say, oh well, whatever happens, what happens, and we lose our humanity and we lose our agency. So on that, I'll finish that and stop sharing, and I'm very happy to take any questions. It's fine, absolutely fine if there are no questions. I can share this. I will send the slide. I will send the slides to Dr. Fatah, and so feel free to email me with any questions about that. And once again, it's been a great privilege to be able to address you today. Thank you very much.